Okay, so in this problem, what we're after is we're trying to figure out basically the motor speed, the torque, and the mechanical power, first of all. So the speed is similar to what we did before. We have a slip of 4%. We have two poles at 60 hertz. So our motor speed is going to be equal to 60 times 60 times 0.95. So we see that that's going to be equal, 0.96. We have a 4% slip. So our motor speed is equal to 3456 RPM. Okay, now we're done with the easy part. Now going after torque. So let's kind of list up what the steps are in figuring out what the torque is. So one, equivalent circuit. Two, we're going to divide up our our equivalent rotor resistance. Three, we're going to calculate the power in the resistor. And then 4 multiply by 3 because of the 3 phases. And then 5 PM is equal to torque times speed. So we're going to get torque is equal to PM divided by our speed. So that's the process that we're going to do. Okay, so let's start with number 1, which is our equivalent circuit. Okay, so what we're going to have is we are going to have our voltage, which is V line to neutral. We're going to have a resistance, a leakage inductance, a magnetizing inductance. In this case, we don't have any core resistance, any hysteresis loss or any of that. And then we have a rotor stray resistance, and then we're going to break our rotor resistance up into 2. Well, let's start with 1 so we can kind of show that effect. Okay, so let's start with our stator resistance is 0.5 ohms. Our stator leakage inductance is 0.6. Our magnetizing inductance is equal to 28.5. And then our leakage rotor inductance is 0.83. And then this is going to be equal to our rotor resistance, which is 0.45 divided by S, which in our case is going to be 0.45 divided by 0.04, which is equal to 11.25 ohms. Now this resistance is going to be a combination of our power, our resistance of the rotors, and the equivalent resistance of the work itself. So we know that if S equals 0, if S equals 1, If s equals 1, then the rotor isn't moving at all. And if the rotor isn't moving at all, then all of our power has to go into electrical heating loss because there's no mechanical work being done. So in this case, RR is going to be equal to 0.45. So we have to take out the 0.45 out of that. So what we're going to do is we're going to take this resistor and break it down. Wow, that's a very bad resistor. Into two resistors. Okay, so then this one is going to be 0.45, and then this part is going to be whatever is left. So this is going to be the 11.25 minus the 0.45. So then this is going to be equal to 10.8 ohms. Okay, so now we have to try and figure out how much power is getting consumed in this resistor right here. Okay, so this part was number 2. Okay, so number 3 is we're trying to calculate power. Okay, so now this is going to be basically a circuit analysis problem. So first of all, our V line to neutral is going to be equal to our V line to line divided by the square root of 3. So we have a line to line of 208 divided by the square root of 3. So this is equal to 120 ohms. Okay, so now we have our big circuit. Let's redraw our whole circuit. So this is 0.5. This is J 0.6. This is J 0.83. J 28.5, 0.45, 10.8. So we're trying to find the power in that resistor. So let's use node voltage, and we will call this V1. And we're going to go V1 minus 120 all over 0.5 plus J 0.6 plus V1 over J 28.5 plus V1 over 11.25 plus J 0.83 is equal to 0. So then we have V1 times 1 over 0.5 plus J 0.6 plus 1 over J 28.5 plus 1 over 11.25 plus J 0.83 is equal to 120 over 0.5 plus J 0.6. And then we are just solving for V1. So calculating what V1 is, we get 1.121 times 10 to the 2 minus J 3.38 times, just 3.38. Okay, so now that we have the voltage, then we can either just, let's just go ahead and calculate our current. We're just going to call this I of our load. So I of our load is going to be equal to V1 divided by 11.25 plus J 0.83, which is equal to, and so we get an IL equal to 9.89 minus J 1.03. And then we're trying to find the power in the 10.8 ohm resistance, which is our load. So now we're going to go IL magnitude squared times 10.8, which is equal to 1.07 kilowatts. Okay, so this is equal to my mechanical power that gets delivered to the load. Okay, so now we have to multiply this times 3. What are we on? Step 4. Which is equal to 3.2 kilowatts. Okay, so that's my mechanical power. I'm after my mechanical torque. So I'm going to go torque is equal to P mechanical divided by omega. Now for these units, omega needs to be in radians per second. So 3.2 times 10 to the third divided by, and then we had 60 times 0.96 times 2. Well, let's go. The synchronous omega times my 1 minus my slip, my 4% slip. And this is equal to 8.85 Newton meters, which is equal to my torque. Okay, so now we have our torque, speed, mechanical power. Here was my mechanical power. So we have our mechanical power, 3.2 kilowatts, torque of 8.85 Newton meters, and our speed was 3,456 RPMs. So now the last piece is just our efficiency. So our efficiency is just going to be our total power is just going to be my P electrical is going to be equal to 3 times my V line to neutral magnitude squared. We'll call it S. Is going to be 3, because I have 3 phases, line to neutral squared, V squared over Z over Z conjugate. So then we just have to find our total impedance. So it's going to be these 3 in parallel with that, in parallel with that. Is going to be 1 over so this is going to be our rotor resistance or rotor impedance plus our magnetizing impedance plus our stator impedance and all 3 of those added in parallel. So that gives me a total impedance of 0.4841 plus J 0.5466. So now my electrical complex power is going to be 3 times 120 squared divided by Z total conjugate, which is equal to Okay, so I made a mistake, so I got to go back and fix my mistake. And my mistake is that you can see that this is Z of my stator. And then I'm going to have these two are in parallel. So my Z total is going to be Z of my stator plus the Z magnetizing in parallel with the Z of my rotor. Okay, so what we have is we have so let's fix this. So this is equal to 9.76 plus J 4.96. Okay, so now my S total is equal to 3 times my 120 squared times my Z total conjugate, which is equal to 3.52 times 10 to the third plus 1.787 times 10 to the third. So now we see that our efficiency is equal to this, the 3.2, divided by this, which is the 3.52, which is equal to 90.9% efficient. Okay,